Hi students, welcome to 6.4 where we're going to be solving linear inequalities using addition and subtraction. You may notice, I think it's about 3 units in a row now, the progress, or sorry, the progression is kind of the same. We discuss the concept at hand, and then we usually look at that concept with regard to addition and subtraction, and then we look at it with regard to multiplication and division. And as you can see, this is no different. So we should know by this point what an equation is. We should know what an inequality is. And we should be able to work with polynomials within inequality statements. And now we're just going to look at what addition and subtraction does to these expressions when we're expressing them in terms of inequalities instead of equals, right? Equation. So if we use a number line, and we have actually looked at this a bit in 6.3, and we start out with two numbers and just make a statement, an inequality. -2 is less than 4. We know that's true. And if we add the same number to both sides, we note that the jumps are the same and in the same direction, which means the resulting inequality is never going to change. So we started with -2 is less than 4, which was true, and then we ended up, when we added 2 to both sides, with 0 and 6, and 0 is still less than 6. So we don't need to switch the inequality sign, whether it be greater than, less than, greater than, equals to, less than, equals to, with addition and subtraction. So that makes it nice and easy. As you can see below, the exact same thing holds true with subtraction. So if we started out with -2 being less than 4, and then we subtract 1 from each side, we find that -3 is still less than +3. So that, that makes it easy, I think. For addition and subtraction, we don't need to flip the sign when we're doing simplification of polynomials. So that is, it's just a property of inequalities. We don't need to change the sign for addition and subtraction. That's basically all you need to know for this page. The rest is just doing addition and subtraction. Instead of using an equation, though, we're going to be using an inequality, and we're usually going to be graphing that inequality. Because remember, one of the focal points from 6.1 to 6.3 is that when we work with equations, we have only one solution, and that's really the key there. If we're solving for h up here, h has to equal 2. If h doesn't equal 2, then the whole thing is sort of wrong and false. Whereas in an inequality, we're coming up with many, in fact, usually infinite numbers of answers. So we're still solving in a similar manner. We're trying to isolate the variable on one side of the sign, in this case, a less than sign. So we wanted to get the h alone, and we found that when we subtracted 3 from both sides, we got h is less than 2. So if h is less than 2, there's an infinite number of solutions that could fit for this, because there's an infinite amount of numbers that are less than 2. What's less than 2? 1.9, 1.8, 1.79999 to infinity, right? So that's why we have to represent it with the or we have to keep in mind that there are many solutions, and often we use a number line to represent that. So we'll just practice a few more. I think I changed this to 2 in a couple of the other units. If you could check it with 2 numbers, it's probably pretty good. So let's solve this inequality, and this is stuff that you've been doing for 3 units now. So the only thing I would recommend is just, be careful. Don't make silly sign mistakes. Don't make silly addition or subtraction mistakes. But you should know the process by now. So what we want to do is we want to isolate the variable. The variable is the x, and then we've got 2 constants. We've got a 6.2 and we've got a -4.5. So what we should try to do is, our x is positive on the right side of the equation, so why don't we bring that -4.5 to the other side? And we can do that by adding 4.5 to both sides. And it doesn't matter that this isn't an equal sign. We still solve our expressions the same way, or simplify our expressions the same way. So we've got adding a 4.5 to both sides. Well, that's going to get rid of the one on this side. That was the whole point. And we know with addition and subtraction, we don't need to change the sign, right? So because we were adding 4.5, we didn't need to change the sign at all. So I just left it as less than or equal to x. And then if we look at the other side, we've got 6.2 plus that 4.5, which is going to equal a 10.7. And I think we also discussed that you have to be careful when you see the variable on the right side of the inequality, because it probably means the opposite of what of what you think it does. When we were talking about equality statements, or equations, I told you several times that it doesn't matter which side you write the variable on. If h equals 2, 2 can equal h. You can switch them back and forth. It doesn't matter at all. But you can't do that. You can't do that with an inequality unless you change it. Because what we're saying right now is 10.7 is less than x, right? Which is actually different than saying x is less than 10.7 or less than or equal to 10.7. So when you flip these around, and you should when you because it makes it easier to graph, you have to remember to flip sides, right? So if you're going to do one of these, make sure you flip the sign. So instead of 10.7 being less than or equal to x, what we're going to say is x is greater than or equal to 10.7. Again, that shouldn't be new because I think we did go through that in 6.3. So let's check this and make sure we didn't make any mistakes along the way. And you can also check it with sort of the version before you flipped it to make sure that that makes sense as well. So if x is going to be greater than or equal to 10.7, I'm going to verify it before I put it on the old chart here, or number line. So I'm going to work with my original statement. Okay, my original statement was 6.2 is less than or equal to x minus 4.5. Okay, let's substitute in x equals 1 on that one. And we start with 6.2 is less than or equal to 1 minus 4.5. So we've got 6.2 is less than or equal to, oh, what am I doing here? This doesn't check anything at all, does it? In fact, it's kind of pointless, isn't it? X has to be less or greater than or equal to, 10.7. Geez, I wasn't checking anything at all. So, in the mistake I made is I picked a value of x that didn't conform to what my statement was. I said that x has to be greater than or equal to 10.7. And then I went and picked x equals 1, which wasn't going to change a thing. So I'm going to pick a number that's greater than or equal to 10.7. So I'm just going to pick 20. Okay, that's just a random pick that was greater than 10.7. So in this case, I've got 6.2 is less than or equal to 20 minus 4.5. 20 minus 4.5 is 15.5, and this is still true, right? So 6.2 is less than 15.5, so that checks. That's one check. So let's do another one. So I checked x equals 20. Maybe I should check x equals 10.7. Why don't I check that? Because I said that it can be equal to 10.7 too. So this one should work out well as well. So we've got 6.2 is less than or equal to x, which I'm going to say is 10.7, minus 4.5. All right, so nothing changes on this side, 6.2. And then 10.7 minus 4.5, as you can well imagine, actually does equal 6.2. So this statement is still true because 6.2 is equal to 6.2, so that's still true. So I checked two values that were greater than or equal to 10.7, and they both checked out fine, which means I've verified it, and now I'm probably pretty comfortable putting it on my number line. So if x is greater than or equal to 10.7, I'm going to start with my 0 maybe right about here, and let's say each of these is 3, so that'd be 3, 6, 9, 12, 15, 18. I probably didn't need to do it like that. I'm going to pick a different number, sorry. Change my mind. So 2, 4, 6, 8, 10, 12, 14. Yeah, that'd be lots. Okay, I'm going to make them 2 instead of 3. So that'll be 2, 4, 6, 8, 10, 12, 14, 16, 18. And then over here we would have negative 2. So it's 10.7. So it's going to be, this is 11 in the middle here. So 10.7 is going to be closer to 11. So I'm going to put the circle right there, and I'm going to fill it in. And I'm also just going to put a little note there that is indeed 10.7. And then because we assume it's continuous data, we're going to go all the way to the end and make sure that we've got our arrow. And I should have done it in red because you want to be sure that you can tell the difference between, you want to make sure you can tell the difference between the original number line arrow and the arrow that you put on to show the inequality. So this includes 10.7, but it also includes the infinite amount of numbers that are greater than 10.7. Now we're just going to do a word problem. That was the whole point behind us doing those extra word problem exercises and using the 5 steps, because you're going to run into a lot of word problems, and those are the most, tend to be the most practical mathematics questions we get, because ideally they relate to something you might see in real life. So Jake's going to board his dog when he's away on vacation, and he's got 2 options. So boarding house A charges $90 plus $5 per day, and then the second one charges $100 plus $4 per day. So what we need to know is how many days must Jake board his dog for boarding house A to be less than, to be less expensive than boarding house B. So what we're looking at is how many days. So if we're going to choose a variable, let's let D equals days, because that's the variable we're going to need. And then let's look at our the information they've given us, and then let's see what is it that we're actually trying to prove here. We're trying to prove that how many days, how many days does it take for house A to be less than, so less expensive than house B. That's not actually an equation. That's just me kind of organizing my thoughts. In order for us to make the actual equation, we have to use the very specific information that is given to us here about boarding house A and boarding house B. So let's do that now. Let's look at boarding house A. So for house A, there's a fixed cost, which means there's a cost you pay regardless, which is $90, right? So let's just put that out front, $90, and then there's a $5 per day fee. So your total cost is going to be the $90 that you have to pay regardless, plus $5 for every day. So 5 times D would be $5 for every day. So that's going to be your total cost for house A. Now for boarding house B, it's a very similar process. It's just different numbers, right? It's $100 a day, or sorry, $100 is the fixed cost, and then the variable cost, the thing that changes, is the $4 per day instead of $5 per day. So I've got 2 expressions, and then I know how to put these expressions together because I did this little mental exercise up here. So what I'm going to do now is I'm going to solve the problem. I set my variable, and then I figured out some expressions based on what they told me in the question, and now I'm going to use them to actually solve the problem. So here's going to be the inequality statement. What we care about is how many days is it going to take for house A's total to be less expensive than house B's total. And remember, these expressions that we made here, those are the totals. That's how you figure out the total cost for each. So what we care about is house A, being less than, not less than or equal to, it says less expensive than. So we need house A to be less expensive than the total for house B. And that's going to happen at some particular values. And I say values because it's not equals, it's an inequality. So there's going to be a certain range of days where it's going to be cheaper to go with A than it is with B. So let's figure out which it is. Well, we have to isolate the variable like we always do. And the easiest way to do that is going to be to bring the 4D over to this side, right? Because you always want to have your variables on the left side of the equation for these. Otherwise, it's too easy to make a mistake and graph it incorrectly. So I'm going to subtract 4D from both sides. I'll leave the 90 for now. And then 5D minus 4D is just D. And then over here, I've still got the 100. Okay, the only thing that canceled was that. So I've got 90 plus D is less than 100. Well, I should probably get that 90 to the other side. So I will subtract 90 from both sides. That cancels there, and I'm left with the final answer, which is D is less than 10. So what I'm saying here is, as long as, what's his name? Jake needs to be gone for less than 10 days, boarding house A is going to be cheaper for him. If he's gone 10 days or longer, then he should pick house B. Let's check that. Let's just check this. It doesn't say to verify up here, but we should always verify. That's part of our 5 steps, right? So let's verify. And I should verify using 2 values for D, right? Normally we'd say X, but this time it's D for days. So let's say we need to our D, in order to check, it needs to be less than 10. So let's check with days equals 1. So if Jake has only gone for 1 day. Okay, so if Jake has only gone for 1 day, our original equation was 90 plus 5 times D, so D is going to be 1, and is less than, and then it was 100 plus, forgot something here, I forgot to put a plus sign. 100 plus 4 times D, which is 1. So in this case, we've got 90 plus $5 is $95. That's the total cost for 1 day. And over here, we've got 100 plus $4 is $104. So I think we can agree that house A is still cheaper than house B. So this still holds. D is less than 10. Yes, it is. And A is cheaper than B. So let's check it with 9, okay? Because we said D has to be less than 10. Okay, so let's check it with 9. So now we've got $90 plus $5 times 9 days. Okay, is that indeed less than $100 plus 4 times 9 days? So we've got 90 plus 45 here is $135. And then over here, we've got 100 plus $36. So that would be $136. So you can see it still holds true. $135 is less than $136. So both of those checked out. Okay, again, even though it didn't say verify, for a word problem, you should always make, that's one of your steps. It's one of your 5 steps, so you should do it. Let's graph the solution. Okay, I made a bit of a mess over here, but hopefully it's not going to worry us too much. D is less than 10, so let's make sure that we've got 10 over here somewhere. I'll put my 0 here again, and I'll go 2, 4, 6, 8, 10, 12, 14, 16. I could keep going, but I don't want to run into that other stuff. And, oh, -2. Is it possible to board a dog for -2 days? Clearly it isn't. Time, as far as we know, only moves forward. And the other thing we have to consider is this discrete data. And in this case, I think it is discrete data because you get charged the $90 or the $100 regardless. That doesn't have any, it doesn't make any difference how many days you stay. And you're either getting charged for a full day or you're getting charged, or you're not. So there's nothing in the problem that says you get charged for a half day or a quarter of a day or whatnot. So I think it's reasonable to assume that you either get charged for a full day or you don't. So you're either there 5 days or 6 days or 7 days. I think that makes sense with what we know about the problem. So I think this is another one where we read it carefully, and I think I think it's very safe to say the data is discrete and can't be negative as well. Right, so that leaves us with, what do we do here? If D is less than 10 and D does not include 10, we could circle the 10 but not fill it in. We could circle 9, 8, 7, 6, 5, 4, 3, 2, and 1. Okay. And I mean, I guess theoretically, we could also put a dot at 0 because, realistically they wouldn't charge him if he spent 0 days, but it would still be 90 is less than 100. So I think there maybe could be a reasonable argument that you wouldn't include the 0 there, but you certainly would have to include 1, 2, 3, 4, all the way up to 9 and not including 10. Okay. So if you look at the answer that we got and just kind of apply a common sense model to it, I think you'll find it makes sense. You can't spend negative days, so obviously the D can't be less than 0. Every day you get charged either another $5 or another $4. There's nothing that indicates there's half days or quarter days or whatnot. So you're unlikely to be charged for 5 and 5.43 days, which also indicates it would be discrete. And from what we checked with our verification, as long as you spend less than 10 days, which in this case would be between 1 and 9 days, it will be cheaper for you to use house A. If you spend 10 or more days, it'll be cheaper to use house B. But the question asks specifically about how many days for house A to be less expensive. And that's what we built our equation on. So our final sentence should be something to the effect of, if Jake uses, let's say, 1 to 9 days, house A is cheaper. Okay, so even in our solution over here, we've got D is less than 10, but we should probably also note that D cannot be less than 0, right? So D cannot be less than 0. Okay. And theoretically, D could not be less than 1, depending on whether or not, again, you wanted to consider a 0-day scenario. So, a very specific example is Jake. If Jake uses 1 to 9 days, house A is cheaper. That's a much better answer than if, it's cheaper if Jake uses less than 10 days. Because if we just say it's cheaper if Jake uses less than 10 days, we haven't, made it specific that we're kind of taking out 0 as a possibility, and we're taking out any negative numbers as a possibility. So that's why I always want you to be as specific as you can. So that's 6.4, and we've only got 6.5 after this. And 6.5, multiplication and division, is going to be a very quick lesson because you knew already half of what you needed to know today from 6.3. And now that you will have practice with addition and subtraction, multiplication will be very easy. Okay, best of luck. Make sure you let us know if you have any questions about this.